Let's take a look at how to name alkanes. So before we get into naming alkanes, I want to just briefly talk about hydrocarbons. So we've talked about hydrocarbons before when we have looked at combustion. Remember, hydrocarbons consist of only carbon and hydrogen. Sometimes we see oxygen added, but usually it's only carbon and hydrogen. So they're always grouped based on the number of bonds between the carbon atoms, and we will see four types of hydrocarbons. We will see alkanes, alkenes, alkynes, and what are called aromatic hydrocarbons. Alkanes are all single bonds, alkenes have a double bond, alkynes have a triple bond, and aromatic hydrocarbons are in a ring structure. So if we take a look at alkanes, alkanes are referred to as what are called saturated hydrocarbons. This means that each carbon is single bonded to four other atoms, either other carbons or other hydrogens. And so we can look at methane, ethane, and propane. So the prefix is based on the number of carbons. So methane, meth means one carbon, eth means two carbons, prop means three carbons. So each of these are saturated because every carbon is single bonded to another atom. So single bond is important for saturation. So the carbon chain can be as long as we want. A different molecule could be made by adding or taking carbons away from the chain. In your notes, you actually have a table that has the first 10 alkanes. Now it's going to be important that you know the prefixes for each of the alkanes. So if you have 5 carbons, that's pentane. If you have 6 carbons, that's hexane. Nonane is 9, decane is 10. So just some real world applications of some of these hydrocarbons. Methane is natural gas. So that's the gas that comes out of gas jets. Propane, that's used for fuel. Butane is used in lighters, and then octane is in gasoline. So we see hydrocarbons have a lot of real world uses. You'll see boiling point here. Boiling point increases as we add more carbons because remember, hydrocarbons are nonpolar, and so the strongest intermolecular force that each of these exhibits is dispersion. And so as the molecule gets larger, it has more electrons, making it more polarizable, and so the stronger dispersion forces results in a higher boiling point. So as we take a look at the formulas here, we can see what are called straight chain hydrocarbons, meaning all of the carbons are in a straight line, or we see what are called branched hydrocarbons. So once we have 4 more carbon atoms, we can make these different molecules. So see here, butane is 4 carbons in a straight line, where isobutane still has 4 carbons, but it's more of this branched structure. These are what are called isomers of each other. Isomers are different structures for the same molecular formula. So these are still C4H10 molecules, but they are connected differently. So we would call them constitutional or structural isomers. As we increase the number of carbon atoms, we increase the number of isomers. And so, for example, decane is going to have many more isomers than butane. So each alkane in the table in your notes differs by 1 carbon and 2 hydrogens, or a CH2 group. The formula for alkanes, this is important. If you know that you have 5 carbons and you know it's an alkane, meaning it's saturated, all single bonds, the formula is CnH2n plus 2. So if you have 5 carbons, you will have 12 hydrogens. If you have 10 carbons, you'll have 22 hydrogens. So based on the number of carbons, you can tell how many hydrogens it has as well. As we look more at organic, we've talked a little bit about these different types of formulas, but we see molecular formulas, so that's just the chemical formula. We see structural formulas. This is a Lewis structure where we see all of the atoms bonded. We see the condensed structural formula, which is when we take the CH groups and we just condense them down, so CH3, CH2, CH2, CH3. And then we have the bond line structure where we use that zigzag format to represent carbon at each end point and corner. So if we take a look at this sample problem, draw the structural formula, the condensed structural formula, and the line structural formula, or the bond line drawing for heptane. So heptane, hep is 7, so that means it's going to have 7 carbons, all single bonded. ANE means it's an alkane, and so it's all single bonds. So if we take a look, if it has 7 carbon atoms all single bonded together, we would see the structural formula having 7 carbons in a row. Every carbon needs to have 4 bonds. And so you have carbons all single bonded, and then fill it in with hydrogens. The condensed structural formula, you just condense all of the CH groups down. And then the bond line drawing, you have 7 carbons in this zigzag pattern. 1, 2, 3, 4, 5, 6, 7. So now we're going to really get into nomenclature of organic compounds. So we use what's called IUPAC nomenclature. They are who come up with the naming rules. And so when we look at naming any organic molecule, a name has 5 parts. Some of these parts we will look at, some of them we save more for honors organic. So 5 parts, we have what's called stereoisomerism, substituents, the parent name, unsaturation, and the functional group. And it actually goes in this order as well. So some molecules we will see have all 5 parts of this. So stereoisomerism indicates whether double bonds are what we call cis or trans. So whether your substituents are on the same side of the double bond or different sides. It also indicates what are called chiral centers. We're not really going to go over this much. We might talk a little bit about cis and trans double bonds, but mostly these stereoisomers are covered in more detail during honors organic. Substituents, so these are groups that are connected to the main chain. So we might see Cl, Br, we might see a methyl group connected. So these substituents are any groups that are connected to the main chain. We will look at a table of substituents that you have to be able to identify and name. The parent is going to be the main chain. So if there are 6 carbons, then the parent name would be hex. If there are 5 carbons, the parent name would be pent. So just knowing those prefixes. Unsaturation will identify if there are any double or triple bonds. So we would look at a different last name. And then the functional group is the group after which the compound is named. So if we actually look at functional groups, we're also going to look at the priority of these functional groups. So this table is on page 10 of your notes. These functional groups we will need to be able to recognize, and we'll talk more about these functional groups as we get into naming different types of compounds. But with these functional groups, they all have certain priorities. Now we're going to focus on naming alkanes. So you notice it's the bottom priority. But if we have something like a carboxylic acid, acetic acid is actually carboxylic acid, but that is a top priority. Alkenes, alkynes are the second and third priority. And so this is actually the priority that we would name them. So we always have to be able to identify functional groups, find them, and then notice how prefix is if it is attached as a substituent. And then the base name suffix is what we would use at the end of a name if this is the top priority. So naming an organic compound. This is any organic compound, and then we'll get more specific into alkanes. So when we name an organic compound, the first step is to determine the base name of the molecule. So the base name of the molecule is determined by the functional groups that are present. So certain functional groups are given higher priority than others. So for example, if you look at the table in your notes, carboxylic acids are the top priority, where alkanes are the lowest priority. So the first thing we have to do is identify all of the functional groups, and then we determine which one has the highest priority. That is going to be based on, that's going to be the suffix, right? The very last part of the name is based on these functional groups. Step 2 is to pick the longest continuous carbon chain in the molecule that contains the functional group, or contains a carbon that functional group is attached to. So when we look for our continuous chain, so the longest chain, if it's 6 carbons or 7 carbons, we have to make sure to evaluate any option. It's not just read from left to right. We might have to go right to left, but we kind of go up, we go right to left and then down. It's not just a quick left to right or right to left. You have to examine all possible options. And then we always want to make sure that if there is more than one way to make the longest chain, we have to make sure that our highest priority functional group is attached to that longest chain. But we always want to keep in mind that if it's a tie, so if we see 6 carbons in 2 different ways, we want to pick the chain that gives the greater number of substituents, so groups that are connected to the main chain. Step 3 is to form the base name. So the base name is going to be based on the number of carbons and the suffix based on the functional group. So for example, if we have 6 carbons, that is hex. But if it's a carboxylic acid, then if you look at the table of functional groups, it ends with oic acid. And so hex and then oic acid would be hexanoic acid. That would be the last part of our name. Step 4 is to number the carbon chain. And so in order to number the carbon chain, we have to make sure we pay attention to the substituents, so the groups that are attached to the longest chain. If the molecule has one of the functional groups that's priority 1 through 4, we want to make sure that we start the numbering closest to that functional group as possible. If it's just an alkane, then we just number on the side closest to the first substituent. And then step 5, describe all substituents that are attached to the main chain and any higher priority functional groups. So with step 5, there's a lot of information in your notes on step 5, but essentially what we're doing is we're indicating the position of all of the substituents that are in the molecule. So it helps some people to circle the substituents, circle the groups that are attached, and list them out. So if you have a priority 1 functional group or a priority 2 or 3, you can see in your notes how we would name it. So for example, ketones, the ending is O-N-E, and we would put the number of the carbon in front. Now this might sound very confusing. We'll look at it as we get into naming alkanes, but your numbering system is going to be important. If you have more than one substituent, you're going to use prefixes like di, tri, tetra, penta, and so on. And then when we actually write the name out. So step 6 is to put everything together and name it. When you put everything together, we use dashes between numbers and letters and a comma between numbers. Regardless of the order of substituents, we always list them in alphabetical order. Some prefixes like di, tri, tetra, those don't count, but iso does count. So we'll look at this again more when we look at naming alkanes. So some other helpful information as we look at alkanes. Remember, alkanes are the lowest priority functional group, but it ends in A-N-E. And so the parent name is taken from the longest continuous carbon chain. So you always need to look for the longest carbon chain. So in this example, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, right? The longest chain is 5. So this would be pentane. Now, some of these substituents that I was talking about, I want to show you some that we see often, especially as we're naming alkanes. We call them what are called alkyl groups. So the ALK indicates that it's similar to an alkane. The YL means that it's attached. So a methyl group is a CH3 group attached to the main chain. An ethyl group, right? F is 2 carbons, so 2 carbons bonded together attached to the main chain. If we have a propyl group, prop is 3 carbons. Now we can also have what is called an isopropyl group. So the isopropyl is attached through the middle carbon. So notice how it's still 3 carbons, just like propyl, but the attachment is different. So isopropyl is attached to the middle carbon, propyl is attached at the end of the carbon chain. So here are some alkyl groups that we'll see. It's going to be really important that you memorize these. These are on page 13 of your notes. So you need to be able to identify a methyl group, an ethyl group, propyl, isopropyl. When it comes to butyl groups, we start to see even more derivations like sec-butyl, right? Sec-butyl stands for secondary butyl. So it's actually attached to the main chain from the second carbon. We have isobutyl, and then we have tert-butyl as well. So it's going to be important that you recognize all of these different alkyl groups, and then here are some other ones that you'll see as well: bromo, chloro, fluoro, iodo, nitro, amino, and phenyl groups. So when alphabetizing, remember, we do not consider prefixes like di or tri. We do consider iso. So now let's focus specifically on alkanes. So we just looked a lot on naming organic in general. Let's look at how to name alkanes specifically. So this means we don't have to worry about functional groups, right? We're focusing just on priority 5, which is alkanes. So step 1 is name the main chain. Find the longest continuous chain of carbons and use that to determine the parent name. It's not always obvious, so notice how when we named this, it was not in a straight line. If I named this in a straight line, 1, 2, 3, 4, 5 versus 1, 2, 3, 4, 5, 6. So 6 carbons is the longest continuous chain. That would make a hexane because it's all single bonds, so it ends in A-N-E. Some people like to redraw it, but others will just name it. Step 2 is to number the carbon atoms. So numbering is going to be really important. Make sure that you're starting at the end closest to the first substituent. So this CH3 group is what we would call a substituent. It's a group off of the main chain. If I number left to right, this is on the 3rd carbon. If I number right to left, it's on the 4th carbon. So you want the lower numbers possible. So we're going to number, in this case, from left to right. The 3rd step is to identify a number, the branching substituent. So since this methyl group is off of the 3rd carbon, right? Since this is off the 3rd carbon, I would say this is 3-methyl. So 3-methyl. If there are 2 substituent groups on the same carbon, then they would both have the same number, right? This would be 3-methyl and 3-ethyl. So then step 4 is to write the name as a single word. So we use hyphens or dashes to separate numbers from letters, and we use commas to separate just numbers. If you have 2 or more identical substituents, then we have to use a prefix. Make sure it is also in alphabetical order. So this would be 3-methylhexane. So notice how it's 3-methylhexane is all one word. For this second example that we had looked at before, right, there was 3. Notice it's 3-ethyl-3-methylhexane. Ethyl comes first because it is alphabetized. And then if we have this third example, numbering 1 through 6, we have 3, right? We have these 2 substituents. This is a methyl group, this is a methyl group. So it's 3, 3 dimethylhexane. Di means that there are 2 methyl groups. So I want you to take a look at the next 3 sample problems. See if you can do them on your own, pause the video, and then come back to check answers. Let's take a look at some examples where we're looking at naming or giving the structures or formulas for different alkanes. So if we take a look at this first one, we want to give the name for the compound represented by this formula. So remember, the first step is to find the longest carbon chain. So if I count 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4. So I see that my longest chain of carbons is 5. So we know if it's 5, that is a pentane. And we know it ends in A-N-E because they're all single bonds. Now what we want to do is we want to number our carbons. So if I number them from left to right, it would be 1, 2, 3, 4, 5. Now it doesn't matter if I did 4, 5 or 4, 5 like this, as long as my longest chain is 5 carbons. Now at this point I would have a substituent off of the 3rd and the 4th carbon. Now if I number it the other way, from right to left, 1, 2, 3, 4, 5, well now I have a substituent on the 2nd and 3rd carbon. So this from right to left is actually the best way to number because it gives the substituents the lowest numbers possible. So if we take a look at the substituents on the 2nd carbon and the 3rd carbon, if I number from right to left, I have a CH3 group and a CH3 group. Well, remember, 1 carbon as a substituent is a methyl group. Again, on the 3rd carbon, this is a methyl group. So when I number this, I'm looking at carbon 2 and carbon 3. So if it's attached to the second and third carbons, those are the lowest numbers possible. So we start the name with 2, 3. So we're listing the numbers where the group is. And then we're going to put a dash. And because these are both methyl groups, we have 2 methyl groups. That would be dimethyl. And those are our only substituents. So then we go ahead and we put the parent name of pentane. So for this first one, it's 2,3-dimethyl pentane. So if we take a look at the next one, we want to give the name for this compound. Now, I give you a hint here, and I said select the longest chain to which the halogen is attached. So we want to make sure that our longest chain has the Cl attached to it. So I could go 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. Well, I see that would be 6. So if I have 1, 2, 3, 4, 5, 6 carbons, that is a hexane. It's ANE because they are all single bonds. Now I'm going to look at my numbering system. So I see that my longest chain consists of these carbons. So I'm just going to try to outline it so we can see it. So when I number it, if I number from left to right, 1, 2, 3, 4, 5, 6, that puts a substituent on the 4th and the 5th carbon, right, off of the main chain. If I number it the other way, it would be 1, 2, 3, 4, 5, 6. So if I number the other way, I have a substituent off of the 2nd and the 3rd carbon. Well, that gives the lowest numbers possible. So I'm going to actually use the numbering system that's in purple because it gives the substituents the lowest number possible. So off of one of the carbons, I have a Cl group. So that is named as chloro. And then off of another carbon, I have a 2-carbon chain substituent. Well, remember 2 carbons is ethyl. Now, when we list our substituents, we have to make sure it's in alphabetical order, not numeric order, but alphabetical order. So if I'm using the purple naming here, chloro comes first with C. So we're going to do 2-chloro, another hyphen to separate numbers and letters. Then we have 3-ethyl, and then we put the parent name, hexane. So this is 2-chloro-3-ethyl hexane. So let's look at one more example. Give the condensed structural formula. Okay, so condensed structural formula, that's not the bond line drawing, but that's going to look like this, right? These are both condensed structural formulas. So it's 1-bromo, 2-ethyl butane. So we're gonna actually work backwards here. I'm gonna start with my parent. The parent is butane, that's 4 carbons. So I'm going to start with the A and E, that means it's all single bonds. So I'm gonna start with carbon, single bonded. There are 4 of them. Now I'm leaving some space here because I might have to add hydrogens. So if I'm gonna have to add hydrogens, I wanna leave some space. So 1-bromo, 2-ethyl. So I'm just going to number my carbons 1, 2, 3, 4. I'm gonna number them left to right. If you're drawing a structure, you can number them how you want. I usually just start left to right if I'm making my own structure. So 1-bromo, that means off of this first carbon, there's a bromo substituent, bromine. Now, does it matter if I put it on the side, on the top, or on the bottom? No. And then 2-ethyl. So off of the second carbon, I'm going to have an ethyl group. Now remember, your C's are what are actually bonded here. So an ethyl group is 2 carbons single bonded to each other. I'll fill in the hydrogens after. So we have 2 carbons single bonded to each other. Now those are my only 2 substituents. So now anything that's left over is going to be hydrogens. Remember, carbon can form 4 bonds. So this carbon has 1, 2 bonds. It's going to need 2 more hydrogens. Now, because it's the condensed structural formula, we're representing all of our carbons and hydrogens like it was up above. So we have CH2. In the middle here, this carbon has 3 bonds. This is going to have 1 more. So it's going to have 1 hydrogen. And then the third carbon is going to be a CH2 group because it has 2 bonds, needs 2 more. And then on the end here, it's going to have 3 hydrogens. Single bond, 3 more. Now for this ethyl group, this carbon has 2 bonds, needs 2 more, so it'll be CH2, and then CH3. Now I know it looks a little weird, I might rewrite it. Maybe I'll erase this and make this CH2 group look a little bit better, but this is the condensed structural formula. So see if you can work through some more of these sample problems with giving the condensed formula or giving the name for these alkanes.